we'll see. So today I'm going to try to tell you about colored vertex model. Okay, and this is a project that I started actually during COVID with 3 students from Berkeley. So David Keating, who was a student of Collier-Reshetkin, Jeremy Metza, a student of Mark Heyman, and Andrew, who was my student. Okay, and today I will tell you about some things that we are doing right now with David Keating, who is a postdoc at the University of Wisconsin and who's going to be on the job market this year. Anyway, so even though I'm going to tell you about the things that we've been doing for the last couple of years, this is part of a kind of a broad topic that is called integrable probability, to kind of mix symmetric functions and vertex model and integrate probability to understand all symmetric polynomials or particle models or things like that. So even though I might not say their names over and over and over, we are not the only ones doing that. So I was last week at a Simons Foundation conference about that. And so it's a very active field. So don't think that whatever I'm telling you is only my ideas. It's going on from many, many people.
Hey, Sylvie, okay. I think my head is floating over the bottom right of your slides.
You don't want to see yourself?
Well, I think I might be blocking part of your picture.
Okay, so let me... okay, but now I lost... okay. Oh, but you're back. I don't...
So I think you just swipe all over to the right off of your screen when he's in the lower right. Or me. There we go.
Yeah, that looks great.
Okay, so I'm going to start with the easiest model of we can think of when we think about vertex model. So there's many types of vertex model, but today I'm just going to stick to the 5 vertex model. So they're always related to integer partitions. So let me just remind you what a partition is. So it's a sequence, lambda 1, lambda 2, lambda k, of non-increasing integers. And we say that it's a partition of n if the sum of the entries of this sequence is equal to n. But today, I'm going to mostly care a way to draw a partition by its Maya diagram. Okay, so you can take, oops. Okay, if I erase my slide, it's not going to work. Okay, so you can take a partition, for example, 4, 3, 1, 0, 0. You can draw its Ferraz diagram where you put a 4, then a 3, then a 1, a 0, a 0. Okay, and then you read just the border of this Ferraz diagram, and I put a particle when I go down, and I put a hole when I go up. Okay, so you're going to have an infinite sequence of particles, followed by a finite sequence of mixed hole and particles, and then an infinite sequence of holes. Okay, and there's one unique way to center the partition that you can see here at this corner. Okay, and you can check that in that infinite world, you have as many particles to the right as holes to the left. So now what's a 5 vertex model? So you just take little squares, little unit squares here, and it's 5 because there's 5 different pieces of the puzzle you can use. Okay, you can have a path going up, a path entering left and going up, a path going to the right, and a path entering down and going to the right. Okay, and now you don't want to only look at puzzle pieces, but you want to glue them together. Okay, so for example, here I take an example where I take an infinite row, okay, where I fix the bottom of my infinite row to be the Maya diagram of a partition mu. So here I just put dots when I have particles. When I put holes, I put nothing. I can fix the left and right border to be empty and the top to be an integer partition lambda. Okay, and it's easy to see that if you fix lambda and mu, there's at most one such a vertex model in the row. Okay, so it's 1 or 0, and if it's 1, if and only if the partitions are interlacing. Okay, so I say lambda is greater or equal to mu if lambda 1 is greater or equal to mu 1, greater or equal to lambda 2, greater or equal to mu 2, etc. Okay, so I really have an interlacing of my parts. Okay, and you can check also that if I just change a tiny bit my vertex model here, if the empty now I change it to a particle. Okay, again, I have at most one way of having this row of 5 vertex model. And it's if and only if now lambda is less or equal to mu. Okay, so if lambda is greater than mu, we put an empty to the right. If lambda is less or equal to mu, we put a particle to the right. Okay, so you can see straight away that if I put several rows, okay, I'm going to have sequences of partition with some interlacing conditions. Okay, so now suppose that I put n rows together and I want them that they form a 5 vertex model. I can now index my rows by variable x1, x2 up to xn. So here n is equal to 4. And then I can give a weight to each puzzle piece. So here, for example, I put a weight x for the puzzle piece where I have a path that exits to the right. And then a weight of a configuration. So I fix all my borders here, empty to the right, empty to the left, mu at the bottom and lambda on top. Okay, and I want to have a configuration that goes from mu to lambda. And then the weight is just the product of the weight of all the vertices. Okay, so for example, here I have an x1 cube because I have 3 paths exiting to the right. And so now after, it's not one configuration I want to count when I fix mu at the bottom and lambda at the top, my number of rows. I want to compute what is usually called the partition function. So I'm going to sum on all configurations that I can do from mu to lambda. And then for each configuration, I get this monomial, okay, this weight of each configuration. Okay. And probably most of you know that already, is that this partition function is actually exactly the skew Schur polynomial in n variable x1, xn indexed by the skew partition lambda over mu. And one way to see that is just to see a simple bijection between these vertex configuration and a skew semi-standard Yang-Baxter. Okay, so you can see that, for example, I have 3 paths exiting in row 1, and I have exactly 3 ones in my semi-standard Young tableau, and so it's an easy bijection to go from this vertex model to the tableau model. Okay, so you can ask, why do I care to translate just this semi-standard Young tableau to a vertex model that we know very well? Is that thanks to that, you have some extra tools, and one of them is called the Yang-Baxter equation. Okay, and what does the Yang-Baxter equation says? I guess I should check the time. It says that if I now take 2 rows of my vertex model, I can find another 5 vertex model indexed by a matrix that I call R, and whatever I put outside, okay, if I fix A, B, C, D, E, F to be occupied to have a particle or not, I can always move the cross to the right, okay? And this R can be written like that. I put its weight, and it's again another 5 vertex model. So I have 5 configurations that have non-zero weight, okay? So in particular, once you have this Yang-Baxter equation, you can prove again that the skew-Schur polynomials are symmetric polynomials, because what you can do is you can take 2 rows of the vertex model, put your R matrix on the left, and you apply the Yang-Baxter equation an infinite number of times until the cross gets to the right. Okay. And so you can do that. So because I have this Yang-Baxter equation, I can take my cross on the left and move it to the right. And then I know that these two vertex models are the same, that they have the same partition function. Okay. And when you move the cross, actually you exchange the label of the rows. So if this row was labeled with xi, now it's labeled with xi plus 1. Okay. And also the weight of this cross that I put on the left here is just 1. And so that means that I can now delete the two crosses and I get the proof of the symmetry of the skew-short polynomial. But I can do other things too, okay? I can, for example, prove Cauchy identities, okay? Just another application of this Yang-Baxter equation. Okay, so now that you are in this setting, okay, what you gain on top is this integrability properties. In particular, one of the tools you can use is this Yang-Baxter equation that give you like all symmetry of the Cauchy identity kind of for free. Okay, these are very special cases of this Yang-Baxter equation. So are there any questions? Okay. So now I want to tell you kind of the same story, okay, the same things that we've done with this 5 vertex model, okay, and I want to do that with colors, okay. So this was during our COVID time, okay, and mostly this was done outside, but now I guess we are back to be able to working together, and that's much better. Okay, so what's a colored vertex model? It's just gonna be, we're gonna take here, I take the example for 2, but we could do that with k colors, okay? So now what I do is I superimpose k different vertex models. Okay, so if I go with 2 colors, I go from 5 different puzzle pieces to 25. Okay, so I can have any of the pairs I had before. So for example, my first color, red, is going straight, okay, and my second color, blue, is entering from the left and leaving on. Okay, now I need to give some weights to this colored vertex model. So first, as I just superimpose my 5 vertex models, what I can do is just take the product of the x weight of before. Okay, so for example, here I have 2 paths exiting to the right, and so I'm going to get an x squared. Okay, and here I have only 1 path exiting to the right, and so I get an x. Okay. But if I just multiply, okay, I don't get something that's very exciting. So I'm just going to get product of short polynomial. So what we add on top is some kind of interactions between the colors, okay? And so whenever a path exits to the right, so I guess here blue would be the smallest color, it counts the number of colors that are in the vertex, okay, and that are bigger, okay? So whenever blue exits to the right, it's get a T if red is present. Whatever red does, okay, whether it turns right, it goes straight, or go up, I always get a T power, okay? So that's my rule. Okay, now I superimpose my 5 vertex models with colors, and now the interactions are just T counts the number of colors that are bigger, that are present in a vertex, okay? And when a smaller color exits to the right. Okay, so that's what I wrote on these slides here. So I don't need to have only 2 colors. I can do it with k colors that are fixed. And for each color, the x weight is just the same as before. But now for each color, I have some interactions. And my T to the flower there is just the number of larger colors that are present in my vertex. Okay. And then we do exactly what we have done for short polynomials. Okay, it's just we put many vertices together and we do configurations and we just take the product of the weights of all the vertices, where the weight of a vertex is just the product of the weight of each color, taking into action these interactions. So let's do a couple of examples. Here I have 3 colors, where I think that red is my smallest color, blue is my second color, and green my larger color. Okay, and the weight of each vertex here is x squared, because I have 2 vertices, 2 colors exiting to the right, and then t squared, because when I left leaves, it has 2 colors that are larger than him, but when green leaves, it's the largest color, and so there's no color that are larger than him. So the red gets an x t squared, and the green gets an x t to the 0. And here blue leaves, okay, so the red still takes a t squared, but now when blue leaves on the right here, it gets an extra t. Okay, and so we are doing the same thing as what we were doing before, except now, so on the left, we choose to be empty, on the right, we choose to be empty. But now we're not going to have only one Maya diagram of a partition. We're going to have k Maya diagrams of k partitions. Okay, so you fix mu1 up to mu k, that are all partitions, lambda 1 up to lambda k. Okay, so and then we're going to do configuration from ui to lambda I, but taking into account these configurations. Okay. And we do exactly the same thing as we have done before for the case of show polynomial. So we count on all the configuration from mu to lambda, okay, where now it's not just one partition, but a k tuple of partition. And we compute the weight of this configuration. And so the theorem that we proved already a couple of years ago is when you do that, what you get is the co-inversion LLT polynomial. Okay, so this partition function, z of lambda mu, is equal to the LLT polynomial. So the skew LLT polynomial indexed by a k tuple of partition. And the same way, before I did a bijection between the vertex model and the semi-standard Young tableau, you can do it like that too. Now the LLT polynomials, they are indexed by a k tuple of semi-standard Young tableau. The co-inversions, so the k semi-standard Young tableau, they are aligned with their content lines, okay? And you can have a co-inversion whenever you find 3 entries, so 2 in the same tableau and 1 in another tableau, okay, that are on this cycle, okay, that u is less or equal to v and less or equal to w. Okay. So let's do an example here with 2 colors, okay, and you can see straight away that it's very easy to see the t weight on the vertex model, because blue here is my smaller color, and so I just need to check when I leave a vertex with the color blue if there's a red on the square. So I have a t weight here, a t weight here, and a t weight here. Okay, so the t weight for this configuration is t to the cube, and you can see that you could translate that into the co-inversions, okay, where the blue dot here would correspond to this co-inversion, so 0 less or equal to 1 less or equal to 1. And the purple dot here would be this co-inversion, 2 less or equal to 2 less or equal to infinity. Okay, so first of all, if you do that, that's a much easier way to read the t powers directly on the vertex model. It's very easy to check rather than looking for those triples. Okay, and again, we're going to have the same tools that what we had before. Okay, in particular, we can again use the Yang-Baxter equation. Okay, and so it's exactly what we had before, and we can prove it combinatorially, that this is the right R matrix. So we can find an R matrix where again, it's going to be a superposition of K5 vertex model. And again, it's simple to read the combinatorial definition of that. Okay, so for each vertex of this kind, and this kind, we're going to add a power of t, where t is going to count the number of larger colors that are of this type. Okay, so for each time you count the number of larger colors that went like that in the R matrix, and that gives you your T power. Okay. So proving it for 1, 2, 3 colors, you can just do it by the computer. But for K colors in general, it's more difficult. And us, we gave a combinatorial proof, but you can also do that using representation theory. And what's behind that is a fusion of vertex. But again, you can do the same things as what we had done for the sure polynomial, okay? Because we have that Yang-Baxter equation, you get for free that this Q LLT polynomial is a symmetric polynomial, okay? And for free also that you have a Cauchy identity, okay? Well, here you have some extra power of T here that I didn't define, but you have a combinatorial rule to get your Cauchy identity also for LLT polynomial. Okay. So it's really kind of a, I don't know, a simple way, okay, to go from sure to LLT just by superposing this vertex models, and you adding now the right interactions between the different colors. Okay. Are there any questions? Okay. So now let me finish my talk by talking about now when we add this condition of being able to wrap around, okay? And now we are not going to have only n variable x1 up to xn, okay? We had the t that we had from the LLT polynomial, but now we are going to have an extra variable q, okay? And again, polynomials are going to be indexed by 2 k-tuples of partition, okay? So simply to go from LLT polynomials to the Macdonald world, you just have to give a bit more freedom to those vertex model. That means that now we're going to be also able to wrap around, okay, to not only see that as a rectangle, but kind of path on a cylinder. Okay, so let me explain to you what I mean by that. Okay, so what I'm going to do is I'm going to do that using an example. Okay, so I have, I guess I wrote in French. So I take 2 partitions. Okay, so for example, lambda 1 is equal to 4, 2, lambda 2 is equal to 4. And I take my 2 partitions mu to be empty. Okay, so I have some starting points. So lambda, my red partition has 2 parts. So it has 2 starting points in column 1 and 2. Okay, and lambda 2 has only 1 part. So there's 1 path that starts in column 1. Okay, and now what I say is I'm allowing my path to wrap around. So for example, my blue path here, it starts here, it arrives at the top, okay, but it hasn't reached the part equal to 4 here, so it's allowed to wrap around. So what do I mean is that it goes around and re-enters here, okay? And then it can go up around, it can wrap again, okay? And by wrapping, that means whenever it exits on the top in a column, it re-enters the same column from the bottom. Okay, so the path wraps around again, and then it finishes, and it's at the end that's prescribed by my blue partition here. Okay, and for the other partition, so this path just doesn't wrap, just as before. Okay, but the other one, it decided to wrap in this column. It wraps around, and it goes here. Okay. And so my claim is now we fix the x and t weight to be as before. So I look on each vertex, I decide its xt weight. Okay, just the same as before. The x when we exit to the right, and the t we count the number of larger corner. But now we have to have a q weight that takes into account the wrapping. Okay, and so that q weight is actually each time it's going to give a q to the distance to the end of the path. Okay, so let's do it on the example here. So I wrap for the first time for the blue path here, but I still have 3 horizontal steps to go to the end. So that gives me a q cubed. And when it wraps a second time, it still has 2 horizontal steps to go to the end. So it gets a q squared. Okay. And my red path, when it wraps, it still has 2 steps to go to the end. So it gives me a q squared. Okay. So if you look, this configuration here, so it has 3 powers of t, and then the weight of q gets q to the squared plus q from the blue color from its wrapping, okay, and q squared for the red color, okay. And you can feel that if you looked at that on like Tableau, okay, if you did the equivalent of that of Tableau, it really feels like what's going on in the modified, the Macdonald modified Macdonald polynomial, okay, because this distance to the end, it feels like the leg statistic, okay. So this is really just a leg statistic that's translated to the vertex model, okay. And then now we do again the same game as before. Okay, we fix a k-tuple of partitions at the bottom, a k-tuple of partitions at the top, and we define these polynomials, okay, h lambda slash mu. And now again, exactly as before, the only thing is now we can also wrap around, okay. The paths are not just exiting at the top and stopping, they can wrap many times, as long as each vertex is still a k-colored 5 vertex. And so when you do that, it's easy because again, you have the same tools from integrability as before to see that this polynomial is always symmetric in x1, xn, and it both generalizing the LLT polynomials and the modified Macdonald polynomial. So for the LLT polynomials, it's very easy with what I said before, because for the LLT polynomials, we had no wrapping. So you just have to set q equal to 0. Okay, and to get the modified Macdonald polynomials and back to the Haglund-Hemandler combinatorial model, okay, for modified Macdonald polynomials, you just have to set all the mu to be empty partitions, okay, and all the lambdas to be just partitions into one part, okay. So Benjamin Young is asking, so the wrapping statistic, it depends on the configuration, because I guess it just depends on the position where you wrap, not on the configuration itself. So, and then what you can do also with this vertex model is something that's also classical, to do some non-symmetric analog. Okay, so I'm going to take the case where mu1, mu k are empty, and lambda1, lambda k are just partitions into one part. Okay, and now rather than making my path starting at the bottom, I propose that they start in a certain order on the left-hand side. So what they are is that they are indexed by an order set partition. Okay, and we do the same thing. We look at the partition functions of these configurations that start at a given configuration on the left and at a configuration on the right, and we do again the same thing as before. Okay, and one application you can do with that, okay, and again, this is just using the Yang-Baxter equation, is that you can see, first of all, that if you sum on all the possible S, you get back to the modified Macdonald polynomial by adding here a small monomial that depends just on S. Okay, so that could be a non-symmetric analog of the modified Macdonald polynomial. Okay, but also something that has been done quite a lot lately, you can also show the link between these non-symmetric modified Macdonald polynomial and some particle models on the circle. Okay, so I guess I'm running out of time, but let me just say that this is something quite related to the tether. So you have n side on a circle. Any side can have any number of balls. The balls are indexed by a partition. And at each time, now we can take an exponential clock that would choose a side. And from this side, a certain number of particles is going to jump. And this is going to be related to the T weight. Okay, so that only works whenever we put all the xi's to 1 and q to 1. Okay, and so you can see exactly how the particles jump. So a particle is going to jump with a certain probability that depends to the weight of the previous particle that jumped. And this again just follows by the Yang-Baxter equation. So again, it's not new that we find relations between these particle models and the world of Macdonald polynomials. So for the classical Macdonald polynomials, that's the work of the asymmetric exclusion process. For some modified Macdonald polynomial models, you can find a tether, and this will present it to you in Davis this summer. And there's many more versions of these particle models that are related to symmetric functions. And so I just cite a few papers here, but this is a very active part of research. And so my time is up. So I'd like to thank you for your attention, and also thank you for giving me the opportunity to give a talk.
Great. Thank you, Sylvie. Let's all thank Sylvie. You can applaud visually or in the reactions buttons or in the chat if you want. And I think we have time for just a couple quick questions. So you can either unmute yourself and ask your question, or you can type your question into the chat and I will read it for you. It looks like Maria has her hand up.
Sure. I have a question. So these paths remind me of the Jacobi-Trudy proof with the sign reversing evolution. I hope I'm not echoing. It's echoing for me. Sorry. So I was wondering if there's any kind of like determinantal formula you can get for these with some sign reversing evolution.
So you get determinant formulas for the Schur case because there's no interactions. But as soon as you have the powers of T, as the path interact, you lose the determinantal process idea.
And Ben has another question in the chat. He wants to know how to read lambda and mu off of the diagrams.
So it's just the Maya diagrams of the partitions that are at the bottom and the top. Does that make sense, Benjamin?
It does. I was just trying to type quickly. Is my audio acceptable?
I can understand you. You're a little growly, but it's okay.
Yeah. Okay. That makes sense. I'm just trying to see. So I read lambda and mu off the top and the bottoms of these diagrams, which is also where I read off the wrapping statistic. So does the wrapping statistic then depend only on lambda and mu, or does it depend on the way that the paths trace through the diagrams?
So it just depends on, so it depends on lambda and mu, of course, because you look how far you still have to go, and it depends where you wrap. But if you fix the places where you wrap, the Q statistic is fixed And then the path can be different.
Right, but the places where I wrap are also the places where the particles in lambda and mu are.
No, I don't count them as particles.
Oh, okay.
Yeah, so maybe, yeah, I guess I put dots. Maybe that was a bad idea. But no, it's really just the path exiting. They don't count in the Maya diagram.
I see. Okay. Got it. That explains everything. Thank you.
Yeah, sorry. So Olia is asking if the process I mentioned is different. So I think it's a bit different in the sense that many balls can jump at one time. So in your tether process, I think just one ball moves at a time.
Okay, well, I think we should thank Sylvie again, because we need to keep the conference on schedule.
Thank you very much.